આજના આપણા સ્પીકર અંકુર કંસાગરા સર અને all the attendees. I welcome you all on behalf of DKV College અને time waste કર્યા વગર I would like to request Dr. Amit Rawal sir to say a few words. Rawal sir.
DKV Arts and Science College ના ઇનિશિયેટિવ સાયન્સ વેબિનાર સિરીઝના બીજા દિવસે આપ સૌનું સ્વાગત છે. પ્રિન્સિપલ શ્રી પુરોહિત સર ના માર્ગદર્શન હેઠળ આપણે આ વેબ સિરીઝ શરૂ કરી છે. સાંપ્રત સમયમાં આપણે આપણી જીવનશૈલી પણ બદલવી જોઈએ અને આ એક એનું બધું ઓનલાઈન આપવાના છીએ. તો આપ સૌ પાર્ટિસિપન્ટ્સ આપણા સ્ટુડન્ટ્સ એ આ વેબ સિરીઝને જો સરખો પ્રતિસાદ આપશો તો આપણે આગળ પણ ઘણું બધું કરવા માટે આપણને પહેલું મળશે. વેબ સિરીઝ જે શરૂ કરી છે આપણે એના માટે આપણે અભિનંદનને પાત્ર છે જાદવ સાહેબ, ભાઈ અક્ષય, એમણે આ વેબ સિરીઝ ઓર્ગેનાઇઝ કરી છે એટલે એ પણ એમને પણ આપણે અભિનંદન આપીએ. જે સ્પીકર્સ છે એ સ્પીકર્સ ગઈકાલે આપણે વાછાણી સાહેબને સાંભળ્યા મેગ્નેટિક મટીરિયલ પર, આવતીકાલે આપણે પંડ્યા સાહેબને સાંભળવાના છીએ અને આજે કંસાગરા સાહેબ બેઝિક ડિફરન્શિયલ ઇક્વેશન્સ પર આપણી સામે વાત કરશે. આપ સૌ આ પ્લેટફોર્મનો ભરપૂર ઉપયોગ કરો આપના નોલેજને રિફ્રેશ કરવા માટે અને અપલિફ્ટ કરવા માટે. તો તું કઈ સમય નહીં બગાડતા હું વિનંતી કરું જાદવ સાહેબને કે એ વેબિનારને આગળ ઉપર ચલાવે. થેન્ક યુ વેરી મચ.
Thank you, sir, for your kind words. This will surely motivate us to perform such activities in future. Now, I would like to request Professor Ankur Kansagra sir to present his talk. Kansagra sir.
Okay, thank you very much. Am I audible?
Yes, sir, fine.
Okay, thank you. I'm really very thankful to the organizer committee for handling such kind of web series. Now, without wasting time, let us start our topic. Topic is basic differential equation. I'll request all the participants to note down my email ID. If you get any kind of query or doubts, you can mail me on this email. So let us start with the definitions of basic differential equation. Before that, I will say what is the outline of my presentation of this webinar. First, we'll discuss some definitions, then some theorems, and finally we will go on examples. So basically this webinar is divided in three parts. First is definitions, second one is theorem, and third one is examples. Now let us start with the definition. What is differential equation? Differential equation is the one kind of equation which involves derivatives of one or more dependent variables with respect to one or more independent variables. So this is the definition of differential equation. Now as we know, there are two types of derivatives, ordinary derivative and partial derivative. So corresponding to that two derivatives, we have two types of differential equations. First one is ordinary differential equation in which ordinary derivative is involved, and second one is partial differential equation in which partial derivative is involved. Right. Next are some examples of these two types of differential equations. ordinary differential equation and partial differential equation. Let us see that this equation involves dy by dx, that means that equation is 10x into dy by dx equals to x plus sin x. Here y is differentiate with respect to x, so x is an independent variable and y is depending variable, right? And here we have ordinary derivative dy by dx, so this differential equation is ordinary differential equation. Second example is again of ordinary differential equation, in which we have d raised to 4x by dt raised to 4 plus y square d2x by dt square plus dx by dt whole raised to 5 equals to a raised to t. Here x is differentiating with respect to t, so this differential equation is ordinary differential equation. Before going to the next equation, which is of partial differential equation, let me bifurcate what two types of derivatives, that is ordinary differentiation and partial differentiation. Now basic difference between them is only the number of variables. That means if depending variable has only one independent variable, then derivative will be ordinary derivative, and if we have depending variable have two or more independent variables, then derivative will be partial derivative. Let us see in example. Next example is d2u by dx square plus del 2u by dy square plus del 2u by del z square equals to 0. Here we are going to differentiate u with respect to x, y and z. So u is a basically function of three variables x, y and z, right? So u is a depending variable and independent variables are x, y and z. So this differentiation will be partial differentiation and equation is going to be partial differential equation. Now next example is again of partial derivative, in which we have del 2v by del t square equals to k times del cube v by del x cube. Here v is depending variable on independent variables x and t, and we are going to differentiate v with respect to t twice and differentiating v with respect to x thrice, right? So again this is a partial example of partial differential equation. So in this way we can bifurcate two types of differential equation, ordinary differential equation and partial differential equation. Next is a order of differential equation. Order of differential equation is the number and which gives us the highest order of derivatives involved in differential equation. So whenever we have to find out order of a differential equation, we have to look what is the highest order of derivative that is involved in differential equation. And next we'll see some examples to find out orders, and next we discuss definitions after couple of slides. But let us define some terminologies. Next is degree of differential equation. Degree of differential equation Degree of differential equation is degree of highest derivative which occurs in it. And to find out degree, we have to first of all remove radicals and fractions from the differential equation. So whenever we have to find out degree, we have to keep in mind that differential equations should be free from radicals and fractions. We'll see in some examples how to do that, but let us consider this as a definition right now. Next definition is linear differential equation. There are two types of differential equations in ordinary and partial, linear and non-linear. Mainly these two types are discussed when we have to solve a differential equation, right? There are some different methods for linear differential equation and there are some for non-linear differential equations. Let us discuss what is the definition of linear differential equation. Linear differential equation is a differential equation in which depending variable and its derivatives have first degree only and no product of depending variable and their derivatives occurs in the differential equation. In other words, we can say that depending variable have and its derivatives have power 1 only, and no product of depending variables with respect to independent variables and its derivatives. And next is a differential equation which is not linear, is called non-linear differential equation. Let us give the general form of nth order linear differential equation. The form of linear general form of the nth order linear differential equation is dny upon dx raised to n plus p1x into d raised to n minus 1 y upon dx raised to n minus 1 plus up to plus pn minus 1x dy by dx plus pnx y equals to r of x. Here y is independent depending variable on x and x is an independent variable, and if we observe the coefficient of d raised to ny upon dx raised to n is 1 here. It's not necessary each and every time that coefficient is 1, but when we say that it's a nth order linear differential equation, then coefficient of d raised to ny upon dx raised to n should be non-zero, and whenever we have coefficient as a non-zero, we can divide with that coefficient to whole equation and we'll get that coefficient as a 1. So here in general it may be written as a coefficient of d raised to ny upon dx raised to n as a 1. One more remark I want to make here is here you can see r of x. Whenever this r of x is equals to 0, then differential equation is said to be homogeneous differential equation. Otherwise, it is said to be non-homogeneous differential equation. There are certain methods, easy methods and easy techniques to calculate solution for homogeneous differential equation, and we'll see that in this session. Now, next is certain examples of differential equation in which we derive order, degree, and whether that that differential equation is linear or not. First example is dy equals to x plus sine x into dx. Here we have when we rewrite this equation as a dy upon dx equals to x plus sine x. Then we have first order derivative of y with respect to x. So order of this differential equation is 1. And to calculate degree, we have to keep in mind that the differential equations should be free from radicals and fractions. Here we in a rewrite form, it is dy by dx equals to x plus sine x. So that differential equation is free from radicals. Radicals means square root, cube roots, 4 root, or in general nth root, right? And it's a free from fraction also. So the highest order is 1, so degree is 1. Now we want to check that whether this differential equation is linear or not. For that, what we have to do, we have to find out independent variables, we have to find out depending variables and its derivatives. Here the depending variable is y, and there is no form of y individually in the form, but its derivative is there, and its derivative is dy by dx, and dy by dx is of power 1, that means it has degree 1. Therefore this differential equation is linear differential equation. Next example is d raised to 4x by dt raised to 4 plus d2x by dt square plus dx by dt whole raised to 5 equals to e raised to t. Now to find out order of this differential equation, we have to find out the highest order of derivative. Here the highest order of derivative is 4 because we have to differentiate x with respect to t 4 times. That is in first term d raised to 4x by dt raised to 4. So its order is 4. Now degree of differential equation means the highest order of uh, highest degree power of highest order. Here the highest order is 4 and its power is 1, so degree is 1. Now let us see it is linear or non-linear differential equation. To check that, we have to observe the depending variable and independent variables and its derivatives of depending variable. Here the derivatives of depending variable are dx by dt, d2x by dt square, and d raised to 4x by dt raised to 4. But in this equation, the last term of the left hand side contains a power 5 of dx by dt. That means we have power not equals to 1 of derivative of depending variable with respect to t. That's why this is a non-linear differential equation. uh, there is one kind of thinking in students is that when some students think that whenever we have degree 1 the differential equation is always linear, but it's not true. Degree is depending on the highest order of derivative, and degree is for all kinds of derivatives of depending variable with respect to independent variable, and this is such example in which we have degree 1 but it's a non-linear differential equation. But yes, we can say that whenever is degree greater than 1, that equation should be non-linear. That means whenever we have degree 2 or more than 2, the differential equation is non-linear. Now next example is y equals to square root x dy by dx plus k times k upon dy by dx. Its order is 1 because we have dy by dx. Now to find out degree, we have to check whether the differential equation is free from radical or fraction or not. Here we have square root of x, but it is the square root of independent variable, and in the definition of degree we have to check whether the depending variable or its derivatives are free from radicals or not. So that square root doesn't affect on degree. But the next term, last term of right hand side, that is k upon dy by dx, contains a fraction form k upon dy by dx. So first of all we have to remove that fraction, and for that what we have to do, we have to multiply all differential equation with dy by dx, and when we do so we get power 2 of dy by dx in the first term of difference right hand side of differential equation, and therefore degree is going to be 2. Now we know that if degree is 2, equations should be non-linear. So this is a non-linear differential equation. Next example is of partial differential equation. Here we have del 2u by del x square plus del 2u by del y square plus del 2u by del z square equals to 0. This is partial differential equation because we have derivatives of u with respect to x, y and z all. Now the highest order of derivative is 2 because we have to differentiate u twice for x. So it is del 2u by del x square, and it's a differential equation of order 2. And degree, again all the derivatives have power 1, therefore its degree is 1, and it is a linear differential equation because all the derivatives have power 1 and no product term is there. Next example is del 2v by del t square equals to k times del cube v by del x cube. This is again order of 3 because we have to differentiate del cube v by del x cube. It is the differential equation with order 3, and its degree is 1 because the power of del cube v by del x cube is 1. And finally it is a linear differential equation because degrees all the derivatives of degree 1 and no product term is there. Next example is of ordinary differential equation, and it is k times del 2y by del x square equals to 1 plus dy by dx whole square raised to 3 by 2. In this differential equation order is 2 because we have d2y by dx square term, d2y by dx square term, because so order is 2. Now to calculate degree we have to check that it is free from radical or fraction or not, but in the right hand side we are given the power 3 raised to power 3 upon 2. So this power is separated by the multiplication of two terms, out of which one is 3 and another one is 1 by 2. So 1 by 2 denotes a square root. So we are given a square root of whole term, and we have to make it free from derivative radicals if we want to find out degree. So to do that we just have to make square both the sides. So when we make a square of that differential equation in both the side, we get in the left hand side as a k square del 2y by del x square whole square is equals to 1 plus dy by dx whole square raised to 3. Now it's a free from radical and fraction also. In that case, in that that means after taking a square of that differential equation, we can see that the power of d2y by dx square is 2, and so degree is 2, and obviously it is a non-linear differential equation. Now if you observe the last term, last equation, without removing a radical, it says that it's a degree 2, right? Sorry, it's a degree 1, because we have del 2y by del x square raised to 1, but actually the answer is degree 2. So whenever we have to find out a degree, we have to remove fractions as well as radicals in the differential equation. Okay, next example is m times del 2x by del t square equals to f of x times t. Its degree is order is 2, degree is 1, and it's a linear differential equation. Okay, now next definition. Next definition is a solution of differential equation. Solution of differential equation. In general, the solution of any equation means a term which satisfy that equation. Now here we have differential equation, so its solution will be some its term will be just a function, and any function is one kind of relation. So its definition is any relation between the depending variable and independent variable which satisfies the given differential equation is said to be solution of differential equation. Another name is integral, because the solution of, to find out a solution of differential equation, we have to make one kind of integration of that differential equation. So solution sometimes is said to be integral. So in general, we just call that solution as a function of depending variable with respect to independent variables. Let us see some examples. In a first example, we are given a differential equation dy by dx equals to 2y. dy by dx equals to 2y, and its solution is y equals to c into e raised to 2x. Now let us see why this y is a solution of this differential equation. Now what does we mean by a solution? Solution is a term which satisfies the given differential equation. So here term is y equals to c e raised to 2x. Now to check whether this y is a solution of given differential equation or not, we have to differentiate y with respect to x. Uh, so when we differentiate it, dy by dx, y equals to c raised to 2x, we get dy by dx equals to c e raised to 2x into the derivative of 2x, that is 2. So after taking a derivative, here we get dy by dx equals to 2 into c e raised to 2x. Now c e raised to 2x, it is y. So when we substitute the value of c e raised to 2x, we get dy by dx equals to 2y. Okay. Now next is an example of second order differential equation, and the differential equation is d2y by dx square plus m2y equals to 0. uh, Here the solution is y equals to a times cos of mx plus b. Here a and b both are arbitrary constants. Now to check whether this y is a solution of differential given differential equation or not, what we have to do, we have to just differentiate y twice. Now a is a constant, so when we differentiate y, a will be as it is, and the derivative of first derivative of cos is minus sign, and the second derivative of cos will be the minus cos. So in the second derivative, that is d2y by dx square, we get minus of m square a times cos mx plus b. Why m square? Because when we differentiate cos mx plus b, we have to use chain rule. That means first of all we have to differentiate cos mx plus b as in terms of cos x, and then we have to differentiate mx plus b. Now the differentiation of mx plus b is m. So in the first derivative we get m, and in second derivative another m. So we get m square. So this y satisfies the given differential equation, and therefore y is a solution of the given differential equation. Next example is a example of partial differential equation. First and second are of ordinary differential equation, and the final one is of partial differential equation. And that solution of the given differential equation, that is del z by del x into del z by del y equals to 1, is z equals to 1 upon a times a square x plus y minus b. Now in a partial derivative, what we have to do, when we differentiate z with respect to x, we have to treat y as a constant. So when we differentiate z with respect to x, that means we want to find out del z by del x. uh, Del z by del z by del x equals to what we get. We have to consider y as a constant, so y and b both are the constants, and derivative of constant is 0. So the differentiation of z with respect to x is going to be a only, because 1 upon a is a constant, so it will be as it is. A square is again a constant, and derivative of x is 1, so a will be cancelled out, and finally we get a as a answer of del z by del x. Similarly, we get del z by del y. Del z by del y equals to, now we want to differentiate y with respect to x, sorry, z with respect to y. So we have to treat x as a constant, so x is constant and b is again a constant, so derivative of that constant is going to be 0, and derivative of y is 1, so del z by del y is just 1 upon a. Now when we multiply these two, del z by del x and del z by del y, we get answer as a 1. So this z is going to be solution of given partial differential equation. Now onwards, we'll discuss for the ordinary differential equations only. That means my further discussion is of ordinary differential equation. I'm not going to take any kind of topic of partial differential equation further. Now next, theorem. So second part of my talk starts here, in which we discuss some theorems. First theorem is the existence and uniqueness of uniqueness theorem, which gives us existence of solution of given differential equation. Let us see what is that. Uh, let us consider the second order linear differential equation, that is a0x y double dash plus a1x y dash plus a2x y equals to r of x. Here if you observe that I am going to use y double dash y dash and so on, they are just the derivatives of y. Whenever we have ordinary differential ordinary derivative, that means in ordinary derivative we have just one variable, so no need to give which with respect to which variable we are going to differentiate. So just so simple short symbol of derivative is y dash y double dash and so on. So here y dash denotes the first derivative of y with respect to x. Y double dash denotes the second order derivative, second derivative of y with respect to x. Here a0, a1, a2 and rx are continuous functions on interval, closed interval ab, sorry, open interval ab, and a0x is not equals to 0 for each value of x belongs to ab, because if a0x is 0, it is not a second order linear differential equation, it is converted to first order linear differential equation corresponding to the values of a1x. Now if c1 and c2 be any two real numbers and x0 is a point in open interval ab, then there exists a unique solution y of x which satisfies the condition y of x0 equals to c1 and y dash x0 equals to c2. Moreover, the solution is defined over the interval open interval ab, right? So this theorem says that if we have continuous functions as the coefficients of derivatives of y and its terms y and its derivatives, then and one more thing, the coefficient of y double dash is not equals to 0, then there always exists a solution, and that solution is unique. So this theorem gives us existence and uniqueness of differential equation of second order. Uh, Next is a corollary. Corollary for homogeneous differential equation. Homogeneous differential equation means here the right hand side is 0, right? In above theorem we have r of x. R of x may not be 0, but in this corollary we have r of x equals to 0. And the theorem says that whenever y or its derivative y dash has value 0 at some particular point x0, then y is identically 0. So by using this corollary, we can say that solution is identically 0 whenever we have y of x0 equals to 0 and y dash x0 equals to 0 for some x0 belongs to open interval ab. Now here if we observe that 0 is obviously a solution of homogeneous differential equation, because whenever we have y of x equals to 0, its derivatives are also 0. So this y dash and y double dash, all these three terms are 0. That's why y equals to 0 is a solution. But this corollary says that no other solution exists if y satisfies these two conditions. So this is a big corollary, and it's sometimes it is used to solve some examples of MCQ types. And we'll do that in this presentation. Next is a remark. In a above theorem, that means in a existence and uniqueness theorem, we had used the condition a of x 0, a0x is not equals to 0. That theorem is not true if we consider a0x equals to 0, right? Let us take an example. Here we had x square y double dash minus 2x y dash plus 2y equals to 6. This is the second order differential equation in which we have a0x equals to x square, and our interval is minus infinity to infinity. That means a equals to minus infinity and b equals to infinity. In that one 0 is there, so a0x is 0 for x equals to 0. Now this differential equation is a solution y equals to cx square plus x plus 3. Now you can check that why this y is a solution of this differential equation. We had do that in this session. But this solution is not unique. Why not unique? Because here c is any arbitrary constant. If you change the value of c, solution is going to be changed. If we take c equals to 0, solution is y equals to x plus 3 only. If we take c equals to 1, solution is y equals to x square plus x plus 3. If we take c equals to minus 10, then that solution is y equals to minus 10 times x square plus x plus 3. So corresponding to different values of c, we have different solutions. So that this differential is not unique because we had not assumed the condition a0x is not equals to 0, right? Next, our theorem in corollary, that means existence and uniqueness theorem and this corollary, they are true for nth order linear differential equation 2. Here we had considered only second order differential equation, but they are true for nth order linear differential equations. Next theorem is says that whenever we have two solution of second order linear differential equation, that their combination is also a solution. So by using two solutions we can generate a third one, right? Here y1 and y2, there are two solutions of differential equation a0x y double dash plus a1x y dash plus a2x y equals to 0. Then its combination, linear combination, that is c1 y1 plus c2 y2 is again a solution, and this is true for any arbitrary constants c1 and c2. So by using that we can say that addition of two solution is again a solution and subtraction of two solution is again a solution. Above theorem is also generalized for n solutions. That means we are given y1 y2 up to yn as a solutions, then their linear combination is again a solution of given differential equation. Now next definition is of Wronskian. In a Wronskian, what we have to do, we have to take n differential n functions f1 f2 up to fn, and that functions are chosen in such a way that the derivative of that function should exist up to n minus 1th order, because we need f1 raised to n minus 1, f2 raised to n minus 1, fn raised to n minus 1. So we need to find out n minus 1th derivative of functions f1 f2 up to fn. So that is the condition for choice of functions f1 f2 up to fn. Now this Wronskian is just a determinant in which we have n rows and n columns. First row is just functions f1 f2 up to fn. Second row is a first order derivative of functions. That means derivative of f1 is f1 dash, derivative of f2 is f2 dash, and derivative of f3 is fn is fn dash. In general, we have to go up to n minus 1th derivative. Here the term power written in bracket denotes the number of derivatives, because when we have to use for first or second derivative we can use dash, but we cannot go up to n minus 1 dash. So the derivative is written in a bracket, open bracket. So f1 raised to n minus 1 denotes the n minus 1th derivative of f1. Now by simplifying this determinant we can have the value of Wronskian. Next definition is of linearly dependent and independent functions. Now this is the definition of linearly dependent functions. Whenever we have linear combination equals to 0 for some non-zero coefficients c1, c2 up to cn, that linear combination is said to be dependent. For example, if we write here f1 minus 3 f2 equals to f3, then this is linearly dependent variables. Why? Because here we have this linear combination f1 minus 3 f2 plus minus f3 equals to 0. So the first coefficient c1 is 1, c2 is minus 3, and c3 is minus 1, and we get the linear combination equals to 0. And why it's called linearly dependent? Because f3 is depending upon f1 and f2. If we change the value of f1 and f2, then the value of f3 is automatically changed. So these functions f1, f2 and f3, they are called linearly dependent variables. Right? Now next definition is of linearly independent. Linearly independent means if the linear combination equals to 0 implies all the coefficients are 0, then that functions are said to be linearly independent functions. Right? Let us make one remark about linearly dependent functions. Whenever we have one function equals to 0, the whole set of functions f1 f2 up to fn, they are linearly dependent. That means one of the function f1 f2 up to fn is identically 0, then that functions are linearly dependent. That set cannot be linearly independent. Now next theorem corresponding to linearly independent and dependent. Next theorem says that if we have second order linear differential equation a0 y double dash plus a1 y dash plus a2 y equals to 0, homogeneous differential equation in which we have two linearly independent solutions y1 and y2. We have a second order linear differential equation, and for the linear differential equation we have linearly independent solution y1 and y2. Then any solution of given differential equation is just a linear combination of y1 and y2. In other words, by using that two solutions y1 and y2, we can have any solution of given differential equation. And this is the theorem which gives us the complementary function in a ordinary differential equation. Right? Okay. Next theorem is between linearly dependent functions and Wronskian. Suppose we have second order linear differential equation and its two solution y1 and y2. Now y1 and y2 are linearly dependent if and only if Wronskian is identically 0. y1 and y2 are linearly dependent if and only if that Wronskian is identically 0. This result is if and only if, and by using this result we can have a remark: whenever y1 and y2 are linearly independent, the Wronskian is non-zero for at least one value of x. So if we find out Wronskian of y1 and y2, and to find out Wronskian of y1 and y2 we have to just find out a determinant in which first row is given by y1 y2 and second one is its derivative, that is y1 dash and y2 dash. So whenever we have to check whether y1 and y2 are linearly dependent or not, what we have to do, we have to just find out its Wronskian. If the Wronskian is non-zero for at least one value, the functions y1 and y2 are linearly independent. Now next is Abel's formula. In this formula, again we have the coefficient of y double dash equals to 1, and that we can do by using division of coefficient. Now this formula gives us a value of Wronskian in the interval I, in which the linear differential equation is defined by using a particular value of x0. Here we are given a differential equation y double dash plus p1x p1y dash plus p2y equals to 0. Again this differential equation is homogeneous differential equation, and its solutions are phi1 and phi2. Now Wronskian of phi1 and phi2 at any point x is just an exponential, that is e raised to minus of integration x0 to x1 p1x dx, w of x phi1 comma phi2 at x0. That means Wronskian of x0, Wronskian at x0, by using the value of Wronskian at x0, we can have the value of Wronskian for whole interval I. Just we need to calculate this exponential term. Okay. Now by using Abel's formula, we have one nice result. Next result: if the Wronskian of any differential solution of any two differential equation is either identically zero or cannot be zero. See, by using the above remark, that means this theorem and this remark, we can say that either Wronskian is identically zero or it cannot be zero for at least one value of x, right? By using this theorem, because when we have two functions y1 and y2, it has only two choices: either it is linearly dependent or linearly independent. If y1 and y2 are linearly dependent, then Wronskian is identically zero, and if they are independent, then Wronskian has at least one non-zero value, right? But by using Abel's formula, we have the nice result which indicates that either Wronskian can be identically zero or it cannot be zero, right? Now we will use this result after in some examples. Now let us discuss some examples. First one is just a differential easy example. Differential equation of the family of curves for radius r whose center lies on the x-axis is. That means we are given a solution. We have to find out a differential equation. So by using a solution, we can get a differential equation. Now let us see how to do that. Its correct answer is 4. Now we know that the equation of circle with center at AB and radius r is x minus a square plus y minus b whole square equals to r square. But here we are given the condition that center lies on x-axis, and on x-axis we know that y coordinate is 0. So in a center AB, b is going to be 0. So the equation of center circle is x minus a square plus y minus x minus a square plus y square equals to r square. Now to find out differential equation, what we have to do, we have to just remove the constant. Here the constant is a. Why a is a constant? Because we have a center on x-axis on which point we are not given. So any point on x-axis is going to be a variable. So here a is a variable and we have to remove it. And for that, what we have to do, just differentiate the given differential equation, and when we do so, we get 2 times x minus a plus 2y dash equals to 0. Here 2y dash is comes from the chain rule, because we have to differentiate y square with respect to y first and then y with respect to x. So when we differentiate y square, we get 2y into dy by dx, and dy by dx is y dash. So we get this equation. After simplifying, we get x minus a equals to minus of y dash. Now substitute the value of x minus a in given equation of circle, and what we get is y square y dash square plus y square equals to r square. And from this, if we take y square common, we get y square times dy by dx whole square plus y equals to r square, and the correct answer is fourth one. Now next example was asked in GATE examination 2013. Uh, Here we have Wronskian of y1 and y2, where y1 and y2 are the solution of given differential equations. Differential equation y double dash plus py dash plus q equals to 0. Now we have to find out a product of Wronskian with respect to product of Wronskian with p, and in the second part we are given some particular values of y1 and y2 which are the solution of given differential equation, and corresponding to that we have to find out p of 0. Now let us see how we do that. The answer of first one is, uh, first of all we calculate Wronskian of y1 and y2. It is just a determinant of 2 by 2. First row is y1 y2 and another one is its derivatives. When we simplify this determinant, that means multiply with y1 with y2 dash minus y2 with y1 dash, and it is not equals to 0. Why? Because we are given a linearly independent solutions, and we know that whenever we are given linearly independent solution, Wronskian is not equals to 0, right? Here y1 and y2 are the solutions of equation 1, that means the given differential equation. It means that y1 and y2 satisfies both that given differential equation, and we get these two differential equation. Now here we want to find out product of Wronskian and p of x. We have the value of Wronskian in terms of y1 and y2 dash. Now from these two equations we just find out p of x, and we use the method elimination method. That means we are going to eliminate q from these two equations, and for that what we need to do, we have to multiply first equation with y2 and second equation with y1, and we take a subtraction of that two, and when we do so we get as a simplified term y2 y1 double dash minus y1 y2 double dash plus y2 y1 dash minus y1 y2 dash p of x equals to 0, because p of x is common in both the terms, so we can take p of x common. Here if we observe the term y2 y1 dash minus y1 y2 dash, it is just a Wronskian of y1 and y2. So when we substitute the value of that here, we get a product of Wronskian and p of x is equals to, this term is going to be on right hand side, so this is the final one, final answer. Now let us go for the second part. From the answer of 1, what we have is p of x is equals to this term. That means from this equation, uh, if we make a p of x as a subject of equation, we get this kind of expression. That means we have to take this one on right hand side and coefficient of p x divide that coefficient. So we get p of x equals to this one. Now what we want to find out in this example is p of 0. So we have to substitute x equals to 0 in this differential equation in the formula of p of x, and here the y1x and y2x are e raised to 2x and x e raised to 2x respectively. Now from that two y1 and y2 we can find out first and second order derivatives of y1 and y2, right? So we have y1 dash, y2 dash, y1 double dash, y2 double dash. Now take x equals to 0 in that terms, we get all these values which occurs in the formula of p of 0. By substituting that values in that formula, we get p of 0 equals to minus 4. So this is the way in which we can calculate p of 0 with just knowing the solution. Here p of x and q of x, they are the arbitrary terms. We are just given a solution y1 and y2. By using that we can get value of p of x and q of x at some particular terms. Now next example, which is again asked in GATE 2007, in which again we are given two solutions of given differential equation y double dash plus py dash plus qy equals to 0. Now here what we have to do, we have to find out for which value of y1 and y2 the p of x and q of x, they are the continuous. Now for that what we do is, we use the theorem in which y1 and y2, they are linearly independent if and only if its Wronskian is Wronskian is not equals to 0. So what we have to do, we have to just find out Wronskian of y1 and y2 for all these four options. and corresponding to which option Wronskian is not equals to 0, that option will be the answer. And here the correct answer is 3, because when you calculate Wronskian of y1 and y2, it is not equals to 0, and so y1 and y2 are linearly independent for the differential equation, and third one is the correct answer. Next example was asked in NET examination, December 2011. We know that in a NET examination we have two types of MCQs. In a part B we have MCQ having exactly one correct answer, and part C we have multiple correct answers. That means it may happen that some answer, one or more than one answer are correct. Now here this example is of having exactly one correct answer, in which we are given y1 and y2 as a two linearly independent solution, right, of this differential equation, and also we are given that x0 and x1 are consecutive zeros of y1s. Now zeros of y1 means when we take x equals to x0 in y1, we get value as a 0. That means y1 of x0 equals to 0. Similarly y1 of x1 is also a 0, and the value of x0 is less than x2, sorry, x1. Now here all these terms x0, x1, all these terms are given. Now let us see the options. The first option says that y1 is of the form x minus x0 into q0, where q0 is continuous function uh, on closed interval AB with q0 x0 is not equals to 0. Or another option is y1 equals to x minus x0 square t0x, where t0x continuous on closed interval AB. And third option is y2 has no zeros in AB. And fourth option is y2 of x0 equals to 0, but y2 dash x0 is not equals to 0. Now here the correct answer is 4, because when we calculate the Wronskian, uh, let me do that. Wronskian is of the form determinant y1, second will be y2, next row will be y1 dash and y2 dash, right. Now if we observe the fourth option, that means y2 x0 equals to 0, but y2 dash x0 is not equals to 0. If what happen if y2 dash x0 equals to 0? In that case, this y2 and y2 dash both have value 0 at x0. So Wronskian is going to be identically 0 at x0, because one column is identically 0 means the determinant is 0, right. So Wronskian of y1 and y2 at a point x0 at 0, and by using Abel's formula we can say that Wronskian is identically 0. Therefore y1 and y2 are linearly independent, sorry, linearly dependent, because whenever we have Wronskian equals to Wronskian equals to 0, they are y1 and y2 are linearly dependent. But we are given that y1 and y2 they are linearly independent, right. So Wronskian cannot be 0, and if Wronskian is not 0, that y1 and y2 dash are not going to be 0. So fourth option is a correct option here. uh, Now next example is again uh, asked in NET examination June 2014. Now I'll request all the participants to take a screenshot of this example, because I'm not going to explain why how we get the correct answer, right. Its correct answer is 1. Now try yourself by using the results which I have discussed in this presentation. By using that result you can get the answer of this example as a 1, right. uh, Now again next example, this is due to Abel's theorem. Next example was asked in NET examination December 2011, and it is a MCQ of the type multiple correct answer. That means this question has one or more correct answers, right. Again I am not going to discuss this example too. Try yourself. If you get any kind of query, I'll tell you, and its correct answer is, again we have to use Wronskian to find out this solution. Correct answer is 1, 2, 3, and 4. That means this example has all correct answers. And this is the problem we have faced in multiple correct answers. We have to check whether all the answers are correct or no, wrong or not. In a earlier case, that means multiple MCQ having one correct answer. If we get one answer as a correct, all other answers are wrong. But here we cannot do so. So we have to check whether all the answers are correct or not. And in this example, we have all correct answers. And finally, thank you. So I'll stop my talk here. Now over to Jadhav sir.
Thank you, sir, for your such kind and useful lecture. અને I'm sure કે આ લેક્ચર જે છે it will be quite useful અને it was very good તમે જે ગેટ અને નેટના એક્ઝામ્પલ શેર કર્યા એ સ્ટુડન્ટ્સને બહુ યુઝફુલ થશે અને I once again thank you all the attendees એ લોકોએ શાંતિથી આ લેક્ચર સાંભળ્યો and tomorrow we will meet on same time for our third and final webinar on transition series method. Thank you all participants. We'll end the meeting now.